Ensemble learning is shaping the way technology impacts our lives. It doesn't just improve accuracy, it creates systems that are adaptable and resilient, even when faced with messy real-world data. Think of ensemble learning as the backbone of modern AI, a technique that's as much about strategy as it is about computation. By the end of this video, you'll see why it's not just a tool for data scientists, it's a way of thinking about problems that can transform how we tackle challenges in any field. So buckle up. We're about to dive into the fascinating world of ensemble learning and discover why it's the secret weapon behind some of the most powerful AI systems in the world. Have you ever wondered why some sports teams seem unbeatable? It's not because they rely on just one superstar, it's because they have a lineup of players, each with a specific role, attackers, defenders, and playmakers, all working together. Ensemble learning works the same way. It's not just one algorithm calling the shots, it's a team of models, each designed to tackle a specific aspect of the problem. And just like in sports, the way you build and manage your team can completely change the outcome. Now, here's the fun part. Ensemble learning doesn't have one way of working. It has three major strategies, each like a different playbook for building that perfect team. The first playbook is called bagging or bootstrap aggregating. Bagging is the defender of the group, the one that steps in to make sure the team stays stable and avoids wild swings in performance. Think of it like this. Instead of relying on just one decision maker, you ask a whole group for their opinions. Bagging takes random subsets of data, trains individual models on each, and then combines their results to produce a stable, average prediction. It's all about reducing variance, so the predictions don't jump around too much. Random forest, one of the most famous algorithms out there, is the poster child of bagging. This technique shines when you have models prone to overreacting, like decision trees. The second playbook is boosting, and this one's a relentless coach. It doesn't just combine models, it actively pushes each one to get better. Here's how. Boosting trains models sequentially, and each new model focuses on fixing the mistakes of the previous one. It's like running drills over and over until the team stops making the same errors. Weak learners, like shallow trees, are turned into strong ones by constantly refining their focus. Techniques like AdaBoost and gradient boosting have revolutionized industries like finance and healthcare because they're so effective at learning from the toughest challenges in the data. And then we have stacking, the master strategist. Stacking is all about bringing together diverse talents. It combines models that think differently, like decision trees, neural networks, and support vector machines, and then trains a meta model to decide how to best blend their predictions. Imagine a conductor leading an orchestra where each musician plays a different instrument, but together they create a masterpiece. Stacking works incredibly well for complex, messy problems where no single model has all the answers. Bagging, boosting, and stacking. Each method has its own unique strengths, and choosing the right one depends on the problem you're trying to solve. But here's the big question. How do you know which one to use and when? Is it always a matter of trial and error, or is there a strategy behind choosing the perfect ensemble method? We're about to find out. Stick with me as we dive deeper into each of these methods and see how they transform raw data into game-changing predictions. Let's break it down step by step. Imagine you're throwing a dart at a target blindfolded. Your chances of hitting the bullseye are slim, right? Now imagine you have 10 friends, each taking a shot, and you average out where the darts land. Suddenly you're much closer to the bullseye. That's bagging in action. Taking multiple attempts, each slightly different, and combining them to get a result that's more accurate and reliable. Bagging, short for bootstrap aggregating, is like having a safety net for predictions. It's designed to reduce the risk of your model going off course by using diversity and collaboration. Here's how it works. Instead of training just one model, bagging trains several models on random subsets of your data. These subsets are created by sampling with replacement, so each model gets a unique view of the data. Once trained, their predictions are combined, usually by averaging for regression tasks or voting for classification. This approach evens out the highs and lows, creating a final model that's far more stable and less prone to overfitting. The star player of bagging is random forest. Think of random forest as a crowd of decision trees, each trained on slightly different data and making slightly different predictions. When these trees vote on the final outcome, the forest produces a result that's more robust and less biased than any single tree could manage. This makes it perfect for problems where individual models are prone to high variance, like decision trees that might overfit the training data. Bagging doesn't just stabilize predictions, it also makes models more resilient to noise. Imagine you're analyzing customer behavior for a marketing campaign. Without bagging, a single outlier, like a customer who bought an unusually high number of products, might skew your predictions. But with bagging, the influence of outliers is diluted, creating a model that reflects the broader trends more accurately. But here's the catch. Bagging works best when your individual models, or weak learners, have high variance. It smooths out their overreactions by letting the team decide. If your models are already stable and low variance, bagging might not add much value. So the big question is, how do you know when bagging is the right choice? And what happens when you need more than just stability? When you need to tackle bias head on? Stay with me, because in the next section, we're stepping into the world of boosting, where models don't just work together, they learn from their mistakes to become stronger. Let's see how boosting turns weak learners into powerhouses. Imagine